category of cobordism precise. Remember, the reason we wanted that was motivated mainly by geometry. I said I want to understand decomposable manifold invariants, and somehow doing this algebraic trick of allowing myself to go all the way down to 0 dimensions seemed to simplify the question. And the second one was, can we classify these? And this is where somehow the algebra will come up and more of the representation theory. An example. Okay. So now, let me try to start giving statements that answer these questions, and then I'll state more of the goals once we have some more words. Okay. So answer 1. This answer is due in many ways to many people. In some sense, actually, the order maybe. I actually think room is the wrong name to put here. Okay, which is and maybe actually even rest. Okay, so there exists a notion of infinity n category. In fact, not just a notion, but the theory of. And cob n, and there exists an example called cob n, satisfying the kinds of things that I said. The vague intuitions from before. So it's kind of weird to state something as a theorem when the result is, hey, we have a way to think about these things and make them precise. There are particular theorems one can state about this, but let me just state it as an answer that definitely took some hard work. Okay.
Why should I expect this to be difficult?
That's a great question that let's address. Well, Greg asked a question, and if you can answer it within the next 10 minutes, then fantastic, you've answered. And if you can't, then maybe you can start answering that question. It's hard. Okay. Actually, that's not a good answer. Why should we expect this to be hard? Let me work a little bit backwards. You know how I defined E2 algebra to be a disk 2 algebra? That's not how it was first defined. Like the first definition, we're kind of stumbling in the dark, and it's a great definition, but we didn't really have this geometric intuition the whole time. And so only in hindsight, can I give you a definition that somehow doesn't use the word, for instance, operac. And so it actually, the hard part, one of the hard parts of this is taking this very algebraic notion of categories with higher and higher morphisms and trying also to reconcile it with the geometric notion. And I hid all that from you when I defined EN algebra. That's one of the huge difficulties. All right, answer number 2 to question number 2, can we classify? And the absurd answer is yes. So answer 2 is what goes by the name of the cobordism hypothesis. I think it was first proposed by Baez and Dolan. John Baez is, I think his background is more of a physicist than a mathematician as far as I understand it. I don't know if that's true. Hopkins Lurie, and the list is sure to grow in names because if you read, for instance, Lurie's paper on this, in the abstract he's quite forthright about saying he gives an outline of a proof. So let me leave it at that. Next time you write a paper where you've proven something and say you've only given an outline of a proof, you let me know. Okay. And so the list is sure to grow. And the hypothesis seems very much true, and it's kind of remarkable. So theorem. So this answer is the theorem. So let's fix C tensor, symmetric monoidal, infinity n category. Let me just say right at the outset that infinity 1 category is the exact same thing as what we've called an infinity category in the previous lectures. So at n equals 1, you can understand at least the hypothesis. Okay. Then there exists an equivalence between the collection of functors, I called it cob. So I can look at cob n, and in this discussion I've been kind of vague about orientations or not orientations. Let me take all of my objects to be framed. That's what this subject fr means. Okay? And I have to tell you what I actually mean by that because some things will change. But I do note that this category, it doesn't just have an infinity n category structure, it also has disjoint unions. And of course I can look at functors into my chosen target, and I can demand that I look at such functors that respect a symmetric monoidal structure. So this symbol just means symmetric monoidal functors. So vaguely speaking, this disjoint union is sent to tensor product.
Can you move up the blackboard?
Okay. There exists an equivalence. So I can look at symmetric monoidal functors from framed cobordisms with disjoint union to my chosen target C. And it turns out that I can more or less fully algebraically articulate what such functors should look like. Turns out there's an equivalence of what I'll tell you in just a second to the collection of what are now called fully dualizable, or sometimes it's also called n-dualizable, fully dualizable objects in C. So that is the statement of the cobordism hypothesis. Okay, so one of the goals of this talk will be to explain what fully dualizable means. I haven't defined that fully well. But to elucidate it, let's start nice and easy. Start with n equals 1. I'm not going to ask if there's any questions about the theorem because you should have only questions right now. That explains nothing. Okay, let's take the example of n equals 1, and let's really take it nice and easy. Let's let C just equal vector spaces over some fixed base field K with tensor product over K. Right? And let's look at a symmetric monoidal functor that I'll call capital Z from the category of framed 1 manifolds with disjoint union. Sorry, from the cobordism category of framed manifolds up to dimension 1 to this category of vector spaces tensor product as its monoidal structure. Okay. I'm still going to be vague about framings and such. Okay, so what are the objects of this category? So there's certainly an object called a point. And you might not think of an orientation on a point as much, but it's certainly a choice of either a plus or a minus. Yeah. The determinant bundle of a zero-dimensional vector space is a line. Okay. So even though the tangent bundle is zero-dimensional, an orientation is data. So let me just call this point plus, which is the positive point. It's going to be sent to something by Z. Let me just call that V. Okay. And whatever point minus is, it's going to be get sent to some other vector space. Let me just call that W for the time being. And if you like, you can think of W as V dual, just as a symbol right now. It just gets to some object W. Okay. Now, up to taking disjoint unions, this is all of the objects in the category of cobordisms, except the empty set. The empty set, because this is symmetric monoidal, it has to be sent to the unit, and that's the base field. Okay? Were you going to say something?
I was confused. When you're talking about the plus and minus on the point, I thought, if I remember right, that the objects are stably framed, so that you would have a frame.
Yes, I will get to that. Yes, I will get to that. Let me just illustrate a principle that happens to be true in this cartoon and also true later as well. Okay. This is exactly what Dan wanted to point out earlier. Okay. I'm doing the same trick as I did for U1 algebras, where certain data just happens to be equivalent even though you need more details. Okay. All right. So now let me just draw some cartoons of what should a functor like that do? So let's say that I have the identity cobordism from point plus to itself, which is the identity cobordism. Certainly Z should send this. Z of this identity cobordism is the identity map from V to itself. Okay. And what I want to note is that actually this boring looking compact one manifold has a very interesting factorization. I can choose to wiggle before I get to my plus point. And I can actually decompose this as so. So I can actually factor this boring looking identity morphism as factoring through some object with 3 points. Okay? So the point is that this composition, let me draw as so. Okay. So this simple visual observation will get us a lot of mileage. Okay. So let me give these maps names. Let me call this horseshoe, let me call it U. And let me call this co-horseshoe, I'll call it epsilon. Okay. So what does Z do to this data? Okay. So note that this first morphism is a disjoint union of two compact one manifolds. Okay. So it sends disjoint union to tensor product. So Z sends the left-hand part of this diagram. Oh, God. Right to left, left to right. All right, whatever. Okay. So it sends this to the identity morphism of V, tensor with whatever Z of U is. Okay. Read this right to left, please. Okay. And then it composes that with whatever Z of epsilon is. Disjoint union is with the identity map of V. Oh, yeah, tensor thing. Okay. And so what this relation says is, so these two one manifolds are obviously equivalent. You can exhibit this equivalence to isotopies in R infinity if you like. And so in the category of vector spaces, there's not much place to send isotopies. Homotopic maps are just the same map in vector spaces. So we have to see that the identity map of V admits a factorization like so. Okay. So so this simple observation is called Zoro's lemma. So lemma. Well, Zoro's lemma. Zoro is not a mathematician; he's a Max Avenger. Z satisfies. So the image of Z picks out maps called U from the unit of your monoidal structure to what I will call W tensor V. It picks out a map that I call epsilon. So U I'm writing as Z of U. Okay. Picks out a map called V tensor W. The unit of your monoidal structure satisfying this condition. Okay, so simple consequence. And now let's see if this puts any restriction on what the value of capital Z can be. Oh, it's called Zoro because Zoro makes a mark that looks like this with this sword.
And the reason the W is coming up is somehow the orientation got switched when you were going around?
Yes, that's right. So this note that the natural tangent vectors coming in here and out are opposite.
Yeah, maybe even at the very top, it should have been point minus on one side.
Say that again?
Like the identity map is actually a cohorism between plus and minus.
No, it's a map from plus to plus. Remember, I demanded that W1's orientation needs to be reversed.
Yeah, I guess I was just like, which one are you labeling?
Okay. Okay. All right. So now let's, so lemma. So in our example of vector spaces, I claim that Z of V must be finite dimensional. Okay. So let's do out a proof of this lemma. It's so explicit. Okay, so here's a proof. So again, let me draw this diagram. This is the way that I think about it. So I have a map from V tensor the unit to V tensor W tensor V to back to the unit. And I want this composition to be the identity map of V. Okay. So out of laziness, so we have this map called epsilon from W tensor V to V. What does it do to an element, lowercase w tensor lowercase v? Let me just call this the pairing between W and V. Oh, sorry, to K. Okay, so I get some real number, if you like, some scalar out of this map, epsilon. Okay. And of course, out of this map U, we get a map from scalars into V tensor W. So let me denote the image of the unit of my base ring as just some summation of VI tensor WI. Like AIJ, VI tensor WJ. But importantly, this is a finite sum. Okay? That finite is the same finite as here. So what does it mean for this composite to be the identity? Well, an element called V under this map is going to be sent to V tensor this summation. Oh, sorry. K is from W. Did I mix things up? Yeah, it's W. I apologize. The worst. Okay. So AIJ, WI tensor VJ. And then this is just sent to the pairing. AIJ and the pairing between V and the WI. VJ. Okay? So this is what the map from V to V does. It sends an element lowercase v to some linear combination of a priori prescribed vectors V sub j. The prescription of these V sub j comes from the definition of U. Right? These Vj are fixed by definition of U. Okay. In particular, remember this is a finite summation. So wherever V is sent, it's sent to some finite dimensional subspace of capital V spanned by the a priori chosen lowercase vj's. So in particular, whatever this map is, regardless of this restriction, it has to have finite dimensional image. But if this is to be the identity, it has to be a surjection, so capital V must be finite dimensional. Okay. And so whatever this theorem is, who knows? Oh, and let me just say that, so now let me state the next part of the theorem.
Sure.
Yeah.
Why is the first summation in this statement? One goes to summation.
An element of a tensor product is a finite sum of generators. Did that answer? Or? Yeah. Okay. So now let me state the next part of the theorem. Z of point plus, which we call V, completely determines Z itself of natural isomorphism of functors. Okay. So the lemma is that there's a restriction, and the theorem is if you choose any finite dimensional thing, then up to natural transformation, you've fully determined everything. Where this pairing allows you to identify capital W as the linear dual to V. So then we have actually proven a baby version of the cobordism hypothesis when n equals 1, and when this is vector spaces. You can actually classify symmetric monoidal functors as equivalent to the collection of finite dimensional vector spaces. Cool. And so the point is full dualizability is a generalization of the notion of finite dimensionality. Okay, cool. I have 20 minutes to cover a lot. Okay. Now let me give a definition. definition, let's fix a monoidal infinity category, which you can just think of as a category if you like. C tensor. And an object V is called dualizable if the following holds. So it turns out that it needs to have a left dual and a right dual. So first, if there exists an object that I'll call VL, together with maps that I'll call unit, the K, to V tensor VL, and I'll call co-unit from VL tensor V to K, satisfying that condition over there. Okay. And then, so that's what it means to admit a left dual. And so, likewise, I'll demand that there exists an object VR, along with analogs of this. So, a right unit map. I'll make this a lot more tractable in just a moment. VR tensor V, and the right co-unit map of V tensor VR, satisfying slot. Okay. In other words, V needs to be exhibited as a left dual of some other object. Okay. Now, let me make the following statement. It's a lemma. If C tensor is not monoidal but symmetric monoidal, turns out asking for a left dual is the same as asking for a right dual, and the left and right dual are actually isomorphic. Okay. So let me write that as a remark so that it's on the board. When C is symmetric monoidal, turns out that any left dual is isomorphic to right dual. And in particular, and dualizability can be checked for just left or just R. Okay. And what we verified in this lemma, in this lemma, is that the dualizable objects of vector spaces are precisely the finite dimensional vector spaces. Okay, cool. So now I need to tell you what full dualizable. Actually, let me give some examples. Okay, so let me give different examples of C and the fully dualizable objects in C. It's going to be an amazing list. So let's take the category of sets with direct product. Turns out that the fully dualizable objects can be fully classified. There's only one called the point. Let me make the remark right at the outset that if your object is the unit for the monoidal structure, it's always going to be dualizable. You can take all of these maps, evaluation, co-evaluation, to just be the identity. Because W tensor V is just a unit again. If W and V are both units. Okay, how about the infinity category of categories? How many dualizable objects does that have? Not very many. It's the trivial category with one object, one identity morphism. What if we take vector spaces, not with tensor product, but with direct sum? Only 0. What if we take commutative algebras over K, tensor product over K, unital maps, you'll only get K. A unit. This is to say that if you take standard categorically well-behaving monoidal structures like direct products, or say co-products in a category, you're never going to have many full dualizable objects. They're all just going to be units. Okay. Let me state one other thing. Let's state, so I haven't defined this yet, but I can pick a category whose one morphisms are algebras, whose objects are algebras and whose morphisms are bimodules between algebras, and I can compose by tensoring. And it turns out that all algebras, so every object in here is dualizable. The point of all this is to say that it's actually quite difficult to find a symmetric monoidal structure where dualizability is both non-trivial and interesting.
Fully dualizable or one dualizable?
These are all one category. These are all infinity one categories.
The last one.
Yeah, this is. Oh, sorry. With isomorphisms. With intertwiners that are isomorphisms.
So what is it again? I sort of missed.
So this is not yet a two category.
But what is alg mod?
It's a category whose objects are associative algebras. A morphism between A and B is just a bimodule.
Okay.
Composition is tensoring over B.
Okay.
You might, be concerned about verifying associativity because tensor product isn't associative on the node, but it's associative up to natural isomorphism. But we've dealt with that kind of issue before. Now you can imagine that you can construct a two category where the maps are not natural not isomorphisms of bimodules, but just maps of bimodules. I am not discussing that here. These are all just one categories. And you're right, I haven't defined dualizability yet. The dualizable objects here are all somewhat silly.
And with that algebra biology, was it K algebras for K of fields, or does it work for a commutative ring?
It works for a commutative ring R. Okay. So now let me tell you what higher dualizability is.
What happened to the finite dimensionality in that last example?
Here, the morphisms are no longer linear maps. They're arbitrary bimodules. Okay. So higher notions of dualizability. There's no way. Okay. So the motivation for this is going to be the notion of adjunction. So recall that an adjunction is the following data. So we have two categories, let's say D and E. We have functors that I'll call D, that I'll call L for left, and R for right. These are functors. Along with natural transformations, that I'll call the unit natural transformation from the identity functor to R composed with L, and a co-unit from L composed with R to the identity. So these are identities of different ones. This is the identity of D, and this is the identity of D. Okay, cool. Such that we have natural maps like so. So what is this first map? I can first apply the identity of L composed with the unit, and then I can apply the co-unit, the identity of L, and I can do it the opposite order. I can do the unit composed with the identity of R. I can do the identity of R composed with the co-unit, such that these compositions are the identity. Okay. So this is the definition of adjunction that doesn't use the home pairing. They don't mention particular kinds of objects. I can take particular morphisms called L and R, and I can demand the existence of two morphisms, which happen to be called natural transformations in categories that satisfy these identities. And so let me just give an example. So let's fix C, a monoidal category, as before, and let's let BC be the two category, where how many objects does it have? It has just one. Okay. What are the morphisms? Well, there's one object. I just need to describe its endomorphisms. It's just going to be the category C. So two categories, collection of objects whose homes happen to be categories. And what's composition? Given by the monoidal structure. Okay. Then in this case, so note, one morphisms are objects of C. And if you trace through what it means for morphisms L and R to admit these units in co-unit maps, then if I have some object V, V is an L or an R, if and only if V is dualizable in the previous sense for objects. Okay. So definition. Let's let C be an infinity 2 category. Then a morphism F is 1 dualizable, sorry, is 2 dualizable. If and only if admits a left adjoint and a right adjoint. So what does it mean to admit a left adjoint? It means that if I put F here, F is some morphism between two objects in a category, I demand that FL be equal to this L, and it has to satisfy these identities. So I want to note that this is a property of F and not data on F. It's does it admit these two morphisms, U and epsilon, satisfying this data. Okay. And then more generally, K-morphism is K plus 1 dualizable if it is 2 dualizable when considered as a 1 morphism in the appropriate category. So what is a K-morphism? It's going to be some morphism between K minus 1 morphisms. You can ask whether or not it's realizable. Okay, so this is completely abstract nonsense. Let's actually see this in practice. So I just erased the cobordism hypothesis, which is silly. There's an identity functor from cobordisms to itself. And in particular, if you believe the cobordism hypothesis, if I take C tensor to be the cobordism category, then the identity functor should give rise to a fully dualizable object in Cobb. Okay? So here's the only example that's somehow pictorially digestible. And I promised Dan that I will talk about the subtleties of things. Let me first prove it for the order.
So we did one dualizable and dualizable and K dualizable. Did you do fully yet?
Oh, sorry. Definition. An object inside some infinity n category that's symmetric monoidal is fully dualizable. Thank you very much. If and only if. So let me call that object X. So first, X is dualizable. Then these maps are 2 dualizable. But to exhibit the 2 dualizability of that, we use the existence of certain two morphisms. And if all of these are K dualizable, or all the way up to n. Okay. Where an object X is called not just dualizable, but 1 dualizable, for instance. So full dualizability, this n is supposed to correspond to that n. That's the convention. So for a 1 category, all you need to check is that an object is dualizable. Okay, but let's draw a picture because this is really, really confusing. So note that in exhibiting the dualizability of positive point in Cob 1, we used morphisms that look like this. Earlier I made the remark that any unit is going to be a dualizable object, and in particular the identity morphisms which we also used are already trivially dualizable. We don't need to verify dualizability for those. But we use these two morphisms. This is the claim. These two morphisms are two dualizable in Cob 2. And the way that I'm going to exhibit this is actually drawing the exact same picture that I drew before. Okay.
I don't think you want the line that you drew at the bottom right.
Thanks. All right. So, apologize for the speed at which I'm doing this, because this actually really is a beautiful thing to verify on your own. You'll see that complicated looking manifold called the disk is showing up. Okay, so let me give this a name. I guess the way that I've read it, maybe I want this to be the unit. Okay, so there's a map from the unit to this thing called the horseshoe with a circle. Okay, so you can read this morphism like this if you like. Okay? So this is a composition of U with the circle. Okay? And so, of course, the circle, there's actually a framing issue that you need to be careful about. I'm going to ignore it. Circle itself, I've decomposed as a horseshoe and a co-horseshoe. So if your name is Dan Fried, you should be very angry at me right now. I apologize. And what I want to note is that from this, horseshoe and co-horseshoe, which don't touch, there's a saddle that I drew earlier that gives me a map from the identity between these 2 points. And so this is the co-unit of my injunction. And this semisphere, or hemisphere, that is cobordism from the empty manifold to the circle, this is D2. This is the unit. Okay. And now what does this composition look like? Well, you can just shrink this 2 disk away. And you see evidently that this manifold looks like this. Which of course is just the identity from the horseshoe to itself. And in general, to see that any morphism in the cobordism category is dualizable,
You should have prepared slides like in Dan's lecture.
yeah, sorry. So to see dualizability in general, like this is somehow the most absurdly easy thing to see, at least at a first pass. Again, I'm ignoring issues of framings, but it's really convincing that you have all duals in the category of cobordisms. So let's fix a cobordism X and say V to W. Okay, let me just draw this as a line with some hair. So the hair is to indicate some sort of orientation. When I draw the hairs upside down, it's with opposite orientation. Here's what I'm going to do, and I apologize that I couldn't. Okay. Given this hair, I can imagine that, so here's my copy of R in which this cobordism propagates. Because of collaring, I can just rotate this hair, cobordism, like so. This collar. Okay. So this is a co-unit. Now I can just do the exact same trick. I now rotate like this. And this is a cobordism from the identity of V, this composite. Okay. So now when I see this movie drawn out, I just see Zorro's lemma crossed with my original cobordism. And I can just see this isotope to just be the original cobordism X. So this is a sketch of a proof of dualizability. You need to be careful about framings, which I was not at all in this talk. There's a way more that I want to say, but I think at this point you're all probably tired. So I apologize I didn't get through everything. Thanks for listening.
Do we have some more questions or comments?
So we started talking about factorization homology first and moved to TFTs
Yeah.
today.
Yeah.
And we saw two like decomposition sort of properties.
Yeah.
Can you make the connection more precise?
Did I plant you? What the hell does this have to do with factorization homology? Here's a theorem due to Claudia Scheinbauer. So let's fix in EN algebra A. Okay. The claim is that factorization homology, definition, a symmetric monoidal functor as such is called an n-dimensional topological field theory. Factorization homology defines a framed n-dimensional topological field theory. So this is an EN algebra in some symmetric monoidal infinity category. There's no n in this. This is infinity 1. Okay? So the target is not going to be C, but it's going to be what's called the Morita category for EN algebras in C. So the objects here are EN algebras. The morphisms are bimodules with EN-1 algebra structures, and so forth. And the N morphisms are bimodules of the E1 algebras that came before. Okay, and so what is this functor? So if I have a manifold called X in here, so it's going to have some dimension, some K. I was not at all precise about what I meant by framing, but so by framing, it's the data of not a trivialization of the tangent bundle of X, but a trivialization after you direct sum it with a trivial vector bundle. So once you equip xk with such data, this actually equips the manifold xk times Rn with a framing. And hence you can evaluate factorization homology, Rn minus k with a framing, and hence you can evaluate factorization homology on that. For reasons we've already discussed, when we direct product with Rn minus k, this is going to have an algebra structure, an En minus k algebra structure. So in fact, this isn't just an object of C tensor, it's an object with an En minus k algebra structure, which is precisely what a k morphism is. That's what TFTs have to do with factorization homology and vice versa. But whether or not all TFTs arise as factorization homology, that is probably true, but with a different definition of factorization homology. You can ask people like David Ayala, Aaron Mazelby, and John Francis about that. Yeah.
Another question. So related to this, I mean, if you think about your TFT, then so I would imagine then if you take like sphere, and it would define you also in algebra.
That's
because like you have a pair of fence and
right. So let's be careful about which sphere.
Like the top or second to top image.
Right. So the observation that's being made is if I look at the here's a pair of pants. It's a cobordism from these two circles to that circle. So what you're calling a sphere, I'll draw as a circle. And the observation was, hey, whatever I associate to a circle, it looks like it has an E2 algebra structure. Okay. We have to be careful about framings here. This is not the circle with the direct product framing. This is a circle with the framing inherited from the blackboard. This is to exhibit, for instance, the circle. It has to be the boundary of a disk somehow. So you give that framing to the disk. What you say is correct.
And does it relate somehow to it? I don't know, this theorem, or because it's sort of like, if I understand correctly, this theorem would associate to Sn minus 1 like E1 algebra?
Yeah.
So, but here, I mean, like, you have like...
You're absolutely correct. What you seek is what you have found.
So maybe in the interest of the coffee break and the 2 more talks we have before lunch, we defer the other questions to private discussion. So let's thank Hiro again for this.